Okay, today is the day we have to do student class evaluations. So I hope more people show up. Okay, so yeah, please hand in your homework first. Please hand in your homework if you haven't already. Okay, so remember we're okay, let's get started. So remember we're talking about compact sets, right? Somebody tell me what a compact set is. What's compactness, Nick?
When you take over an open set, you have a you have a finite closed semi. What was the definition? You have a subcover. You have a finite subcover. That's the word. Sorry.
Yes, exactly.
You have a finite subcover.
Yeah. So so compactness, right? Compact set, right? So K is compact if given any collection of sets G alpha, where the G are open sets, G alpha are open, such that K is contained in the union of the G alpha, right? Given any set of open sets, given any collection of open sets whose union covers the set, there exists a subcollection, right? A finite subcollection, G alpha 1 through G alpha K, n, say, such that K is contained in the union of those that subcollection. Okay, so given any open cover, there exists a finite subcover. Right? Given any open cover of your set, there's a finite subcover of your set. Okay. Okay. So one of the problems that I had you do for your homework was following: if F is continuous on K, a compact set, then F of K is itself compact. Okay. The continuous image of a compact set is itself a compact set. Okay. The continuous image of a compact set is itself a compact set. Okay. So we want to show that this thing is compact, right? So we say, okay, suppose we have G alpha and open cover of the image. Okay, so there's K, our compact set, right? And then F maps it to some set over here, F of K. And suppose we have some open cover, right? Some open cover of the image. Okay, we want to see that there's a finite subcover of that image. Okay. So how do we? Did anybody figure it out? Nick.
I have a guess, but so you do is you can, since it's a map, you can map that cover, that open cover, back to K, and then you know that K is continuous because K is a subset of R, and it's continuous on R.
Yeah, the K is a compact set.
Sorry, the function is continuous on K.
Yeah.
And then you can say that, and you know that K is compact, so that you can say that there's a finite subcover over K, and then since it's a function, you know it's onto, so that you can remap that finite subcover back onto F of K.
Exactly.
And say
that's perfect. Yeah. So you say, okay, I take my my cover here, and then I look at all the pre-images. Okay. So consider F inverse G alpha. consider the F inverse G alphas, right? The pre-images of the G alphas, right? The pre-images of the G alphas. These guys, right? Since the G alphas cover F of K, K is contained in the union of these pre-images. Right? K is contained in the union of the pre-images, right? And further, these guys are open. Why are they open?
Because they are a union of open sets, and a union of open sets is open.
No. Why? So the G alpha were open, right? Why are the pre-images of the G alpha open? Why is each F inverse G alpha open, Nick?
It's 1-to-1, so you get the function's 1-to-1. So
Not because it's 1-to-1. Not because it's 1-to-1. Anybody remember?
Is this the different definition of continuity?
This is the topological definition of continuity. Remember that's the
Since F is continuous.
Yes, exactly. Yes. Right. So, right. These are open. The F and G alpha are open since F is continuous. Right. We saw that if you're continuous, then the pre-image of open sets are all open. Right. Okay. So then K is contained in K. This is an open cover. The union of these guys, the collection of these guys is an open cover for K. And then since K is compact, as Nick said, since K is compact, we know that K is included in some finite there's some finite cover, there's some finite subcover that still covers K, but then G alpha 1, G alpha n covers F of K, right? And so we've got a finite, we started from our open cover, and we ended up with a finite subcover. So F of K is itself compact. All right, we're just remembering what compactness means, and then doing the homework problem.
Okay, thank you.
Okay, showing that if you have a compact set and you have a continuous function, then the image of that compact set is itself compact. Okay. So the image of compact set is going to be compact as long as the function is continuous. Okay. So today we're going to do a bunch of other properties of compact sets, and that'll be it. We have to do evaluations today because next week we're having the presentations. We probably won't have time to do the evaluations. So other properties of compact sets. I'm hoping that we'll get to. We'll see. We'll see. Okay, so let K alpha be a collection of compact sets. Suppose you have a bunch of compact sets, right? And this is in R. If the intersection of any finite subcollection is non-empty, then the total intersection, the intersection of all of them, is non-empty. If the intersection of any finite subcollection is non-empty, then the intersection of all of them is non-empty. This should be a little bit reminiscent of something you did earlier. Does this remind you of anything? you've got a bunch of sets. Whenever you intersect them, you get something non-empty. The intersection of all of them is non-empty. Do you remember we did some problem like this earlier?
Something like finitely many or something?
No. It was remember if you have nested, closed and bounded nested intervals, right? You showed you showed already that that the infinite intersection of nested, closed and bounded intervals is going to be non-empty. Right. So this is related to that. This is related to that. Yeah.
What's the word after finite?
Subcollection. Sorry.
Subcollection.
Yeah. So collection, subcollection. Let K sub alpha be a collection of compact sets.
Is it
That's an X. Sorry.
oh, sorry, no, it's fine. Is it an infinite collection or a finite collection?
It's an infinite collection.
It's an infinite collection.
So you've got
Okay.
any collection of I mean it could be finite or infinite. Doesn't matter.
Okay.
But the mean of it is if it's infinite. If it's finite, then there's nothing to be done. Yeah.
Is this not a property of all sets in general?
So is this a property? Is this something that all sets do? Can anyone think of a bunch of sets? The intersection of any finite subcollection is non-empty, but the intersection of all of them is empty. Let me give an example because we don't have much time today. So let A sub n be 0, 1 over n. Okay. If you intersect all of these guys, there's nothing in there. Right? There's no point that lies in all of the A sub n's. Right? If I say 0, 1, 0, a half, 0, a third, 0, a quarter, 0, a fifth, etc., there's no point that lies in all of these guys. Right? However, if you intersect any finite guys, well, you just get the smallest one of them. Okay, so no, it's not true for all sets, but it is true for compact sets. Okay, so let's do this thing here is sometimes called the finite intersection property. So if your collection satisfies the finite intersection property, then the intersection of all of them is non-empty. Okay, so we're going to do this proof by contradiction. Suppose that the intersection of all of them is empty. Okay. Suppose that you intersect them all and you get the empty set. Okay. In that case, if you take the complement, you're going to get R, right? The complement of the empty set is going to be the whole set, whole space, right? But here, by De Morgan's laws, right, we've got the complement of an intersection, so that's going to be the union of the complements, right? So by De Morgan's laws, this is this. Okay. So R equals the union of the complements of the sets. Okay. Now, so fix any K alpha naught. Okay, so choose any one of these guys. Call it K alpha. Choose one of these guys and call it K alpha naught. Okay. Then these complements, K alpha naught is contained in the union of these complements, right? Because the complements cover the whole space, right? The union of the complements covers the whole space. Okay. But these guys are open, right? Remember, compact sets are closed, so the complements are going to be open, right? And so what this is, we see that the K alpha complements are an open cover of K alpha naught.
is again what you picked K alpha naught to be?
K alpha naught was just any one of these, any one of the K alphas, right? Choose one of the, choose any one of the K alpha. Call it K alpha naught.
And because K alpha naught is in R, you're saying it's
Yeah.
contained?
Yeah, because this thing covers the whole space.
Okay.
Well, it certainly covers K alpha naught.
Okay.
Right? K alpha naught is in the space, right? So we cover the whole space, we cover K alpha naught, but this is an open cover, and so there's going to exist a finite subcover, right? So K alpha naught compact implies that it's included, it's covered in some finite collection K alpha I from 1 to n. Right? That there exists a finite subcover. Okay. So K alpha naught is contained inside of this guy, right? So in that case, K alpha naught intersect the complement of that guy is empty. Right? K alpha naught is included in this set, so it does not intersect the complement of that set. Okay. Everybody all right? Okay. So now we use De Morgan's laws again, and we say, well, the complement of a union is the intersection of the complements, right? So we'll get the intersection of the double complements. In other words, the intersection of the sets themselves. Okay. Okay. So you get that K alpha naught intersect K alpha 1 intersect K alpha n is empty. Right? By De Morgan's laws. But that's a contradiction. Right? Because we're supposed to have the finite intersection property, right? The intersection of any finite number of these guys was supposed to be non-empty. Right? The intersection of any finite number of these guys was supposed to be non-empty, but here it is empty. Here it is empty. Okay, so contradiction. Okay. Okay. Any questions? Pretty simple. Okay. So this is going to help us to get the following kind of interesting theorem. Any closed and bounded interval is compact. Any closed and bounded interval is compact. And you've probably been suspecting this, right? That any closed and bounded interval is compact. Right? Because we talked about the extreme value theorem, and we said, oh look, you know, the function, continuous function on a closed and bounded interval contains a max and min, blah, blah, blah. Okay. Corollary. Any closed and bounded set is compact. Okay. Now remember earlier we showed that compactness implies closedness and boundedness, right? So what this is saying is that compact is equivalent to being closed and bounded. Okay. Compact is the same thing as closed and bounded. And I should say this is, notice that this is in R. This is not necessarily true in other spaces. But in R, yeah?
So now we're just proving the reverse.
Yeah. So we'll show that, yeah. So we already showed that compact implies closed and compact implies bounded. Okay. Now we're going to show that closed and bounded implies compact. Okay. So we get that in R, closed and bounded is equivalent to being compact. So compactness is the same thing as being closed and bounded. Okay. And we'll get there by showing that any closed and bounded interval is compact. Okay? Let me prove the corollary first. So assume we have this theorem. Suppose that E is closed and bounded. Suppose you have a set that's closed and bounded. Well, since it's bounded, it implies that E is contained in some interval negative n. Right? Some interval for some n. Right? That's what bounded means. Right? Okay. But then E is closed, but then E is a closed subset of a compact set. Right? By the theorem, this is compact. Right? The theorem we're going to prove in a second is any closed and bounded interval is compact. Well, so E is contained in a compact set and it's closed. Right? And we showed last time that if you're a closed subset of a compact set, then you yourself are compact. So it itself is compact. So this is this is not the hard part. The hard part is proving the first part, that to see that any closed and bounded interval is compact. Okay. Okay, so we're going to do proof of the theorem by contradiction. Nick, go ahead and ask you the question.
Okay, I'm back. Sorry.
Yeah.
I was confused about the difference in interval per set.
Yeah. So we are going to now prove that any closed and bounded interval is compact. So, so suppose that, say that I naught is a closed and bounded interval. And that I naught is not compact. Okay. And we're going to get craziness from here. Okay. So, we say, okay, well, being not compact, what does being not compact mean?
Doesn't have a finite subcover.
What doesn't have a finite subcover?
The open cover.
What open
that
cover?
covers I naught.
Every open cover?
Any open cover.
No.
Any open cover?
Just one.
Just one.
Yeah,
Just one. Just one open cover fails, right? Right. So remember, being compact means that every open cover has a finite subcover. Right. Being not compact means that fails. So there's one bad guy, at least one bad cover that doesn't have a decent finite subcover. Okay. So So being not compact. So suppose this guy's not compact, i.e., there exists a bad open cover. In other words, some G alpha such that there is no finite subcover of I naught. There is no finite subcover of I naught. You've got this cover, but for some reason it doesn't have a finite subcover of I naught. Okay, so now we do something funny. We take I naught, divide I naught into two closed subintervals of equal length. Right, so you take your I naught, right, and you divide it into two parts. Right, so here's your I naught, and you divide it into two subintervals. Okay. Okay. So Since G alpha had no finite subcover of I naught, then G alpha must have no finite subcover of at least one of these intervals, right? At least one of these intervals must also fail to have a finite subcover, because if they both have finite subcovers, we're done. That we would have had a finite subcover of I naught, right? So at least one of them, at least one cannot have a decent finite subcover. Call it I1. Okay, so maybe it's this guy on the right, call it I1. Okay. And then you can, you know what we're going to do, keep on doing that, right? Divide I1 into two parts. Well, one of these subintervals must not have a decent finite subcover. And so we get a succession of nested closed intervals, none of which has a decent subcover. Okay? So continuing, we obtain a sequence of nested closed and bounded intervals. I sub n, such that the length of the I sub n is 1/2 to the n times the length of I naught. Right. This absolute value we use as the length of the set. Right. So they're shrinking by half every time, and none has a decent finite subcover. Yeah, Nick.
Sorry, is it none or is that at least one?
None of these guys. None of these intervals that we've chosen has a decent finite subcover.
It's like in the first step you said at least one doesn't have a decent subcover.
Mm-hmm. So, and we chose that guy. We said, the guy on the right, that's going to be our I1. Okay, that guy doesn't have a decent finite subcover. And then we divided I1 in half. And one of these guys, doesn't have a decent finite subcover. We call that guy I2. Okay. Okay, so I naught, I1, I2, none of these guys has a decent finite subcover. Okay. We get I3, also doesn't have a decent finite subcover. We get a succession of guys shrinking, and none of them has a decent finite subcover. Okay, so now my previous problem, we know that the intersection of the IN is non-empty. Right? This was your homework problem ages ago. Right? The homework, the intersection is going to be non-empty, and in fact, it must consist of a single point. X, right? Because the diameter is decreased, right? Because the size of the intersection shrinks to 0, right? Okay. So, right, since the size of the INs goes to 0, right, it must consist of a single point. Then, let's go back to G alpha again. Okay, go back to that open cover. X must lie in a G alpha naught. Right? That point must be covered by somebody, because this is an open cover of the whole interval. Since G alpha naught is open, we know that there exists an epsilon neighborhood of X that is in G alpha. So, right, we take the intersection of all these guys, right, all these, intervals that have no decent subcovers, and there's some x there, right? There's some point x, right, in the intersection. Now, we know that there's got to be one g alpha naught that x lies in, right? Further, that the g alpha naught has to contain some, being open, it has to contain some epsilon neighborhood, right? So there's x, there's g alpha naught, and we know that there's some epsilon neighborhood of x that's contained in g alpha naught. Okay, so now what's going to happen, we say, okay, well, look, now choose n such that the size of I sub n is less than epsilon. Right? This is, the size of I naught over 2 to the n. Right? They're shrinking by halves. Certainly we can choose n big enough so that this is smaller than r epsilon. Okay. Right? But then x lies in I sub n. Right? X lies in I sub n, and the length of I sub n is smaller than epsilon. Right? So that I sub n lies inside of the epsilon neighborhood. Right? And I sub n lies inside of the epsilon neighborhood. Right? But that epsilon neighborhood lay inside of one of the g alphas. But that means that I sub n is covered by this finite subcover. That's a contradiction because all the I sub n's, right, none of them had a decent finite subcover. But here we are, this guy's covered by a single set. Okay, so you get a contradiction. Okay, so this is a pretty important theorem that compact sets in Rn are just closed and bounded sets. Compactness is equivalent to being closed and bounded. Okay. And that theorem is called, so that corollary, right? The corollary that K compact in R is equivalent to K being closed and bounded. Has a name. It's called the Heine-Borel Theorem. The Heine-Borel Theorem. And that's basically the main thing that I wanted to get to today. So I think that's a good place to stop. I was thinking of saying one more thing, but it's probably not be sort of a letdown after that. So this is a good place to close the course. Okay. So don't go away. You have to fill out evaluation forms. Yeah, those of you who came in late, turn in your homeworks if you haven't already. Two things. So the administrative assistant forgot to give the instruction sheet for this, so I'm just going to tell you what the instruction sheet normally says. It says that these course evaluations are used in evaluating the performance of professors, and they're used to judge whether a professor can basically be promoted. So like for people who've been at Scripps, been at a university for less than 6 years, they're kind of in a probationary period. There's what's called an assistant professor, and then they get evaluated. If they pass that bar, then they're called associate professors, and they basically have the right to stick around at that university forever. Right? They're basically unfireable unless they do something really outstanding. And it's happened before in Scripps' history. Anyway, maybe I should turn off the video. Yeah.